Hello everyone, my name is Ansh Shrivastava. I'm currently pursuing my Bachelor's in Technology from National Institute of Technology, Raipur. Today, we are going to study chemical bonding. Chemistry has been one of my favorite subjects, not only because it explains the world around us, but also because how logical and interconnected it is. Chemistry has always been a subject where small concepts have a huge impact on understanding and solving problems. And do you know what? Chemistry is full of such small, easy to understand concepts that can make a huge difference in solving problems. Take a simple idea, apply it right away, and boom, it feels like one of yours. फिर हेरा फेरीज 21 दिन में पैसा डबल scheme. Here's a fact. Did you know that 20% of the concepts in chemistry contribute to 80% of questions in exams? Chemical bonding is one such topic. It's the key to unlocking questions in inorganic, physical, and organic chemistry. Even for me, when I was preparing for JEE examination, getting a firm grip on chemical bonding boosted my confidence and helped me solve tricky problems with ease during the exam. So let's get started with our subject and let's hit the desk. So let's begin our journey into chemical bonding. This topic holds a significant weightage of your JEE syllabus, and not just about marks, but understanding this topic will build you a very strong foundation for your important chapters ahead. In this lecture, we will uncover how and why hybridization occurs, break down its different types, and learn how to apply simple tricks to solve questions quickly. So let's break it down and see how it all works. Yeah, so this is the objective of my session. We will start by understanding the cause of chemical bonding. Why do atoms bond in the first place? We will understand that first of all. Next, we will then explore some types of chemical bonds, and then we will eventually dive into the main topic of hybridization. We will cover its definition, I will explain the topic, and we'll go through some examples and finally learn how to calculate the steric number Z. So let's move ahead. Yeah. So now that we have set the stage, let's dive into the cause of chemical bonding. Why does chemical bonding takes place at the first place? So atoms don't exist in isolation. They interact with one another to form bonds. But why do they do this? So the main driving force behind bonding can be explained by the two fundamental ideas mentioned here. As you can see in the illustrations. So number one is octet rule and number two is to lower the potential energy of the system. Starting with the explanation of octet rule. So atom tends to bond to achieve a stable electronic configuration which often resembles a noble gas configuration, and this is known as octet rule. So octet rule can be fulfilled by two scenarios, either by transfer of electron or by sharing of electron. You can see the visualization to understand it in much better. Both these processes aim to achieve the noble gas configuration, which ensures the stability for the atoms. Reason for bonding, and it is lowering the potential energy of the system. So we know that when atoms come close, they experience two opposing forces. First is attraction, second is repulsion. Attraction between the positively charged nucleus of one atom and the negatively charged electrons of others, and repulsion between the nuclei of the atoms or between the electrons. Now, if we plot the potential energy curve against the internuclear distance, we will get a U-shaped curve as you can see on your screen. Notice that at very large distances, there's a little interaction between the atoms. So the energy is higher. And now, as the atoms move closer, the attractive force starts to dominate, which lowers the system's energy. However, if they get too close, the repulsive force starts to dominate, which now increases their energy again. And the point at which the potential energy is at its minimum represents the most stable distance between the atoms. And this is where bonding occurs. So, in essence, bonding happens because atoms want to achieve the octet rule or a noble gas configuration for stability, and also they aim to lower their potential energy, creating a more stable system. Moving ahead to the types of chemical bond. So as you can see, the chemical bonds can be majorly classified into two categories: interatomic bonds and intermolecular forces. So in interatomic bonds, we have ionic bonds. Ionic bonds occurs when one atom donates electrons and another accepts them. For example, you can see in NaCl, sodium loses an electron to become Na plus, while chlorine gains that electron to become Cl minus. And now the electrostatic attraction between this Na plus and Cl minus forms an ionic bond. Then there is covalent bond. Covalent bond is a bonding in which atom shares electron, not transfer but share electrons to achieve stability. Then we have coordinate bond, which is a special type of covalent bond where both the shared electrons are provided by one atom. Then we have metallic bonds, which occurs in metals. Then we can see intermolecular forces. Intermolecular forces are of two types: van der Waals force and hydrogen bond. Van der Waals force are basically weak force of attraction that actually exist between all the molecules, whether it is polar or non-polar. It includes dipole-dipole interaction, dipole-induced dipole interaction, and dispersion forces. Hydrogen bond is nothing but a special type of dipole-dipole interaction which occurs when a hydrogen atom covalently bond to a highly electronegative atom like oxygen, nitrogen, or fluorine interacts with interacting with another electronegative atom. So these are the two major categories of or we can say types of chemical bond: interatomic bond and intermolecular force. Interatomic bonds are considered to be stronger types of bond with bond energy ranging from 200 to 400 kilojoule per mole, while intermolecular forces are considered to be comparatively weaker bonds with a bond energy ranging from 2 to 40 kilojoule per mole. Moving ahead to the next topic, hybridization. So finally coming on to hybridization, our core concept. So as you can see on the screen, first of all we have to go back to valence bond theory, and you can see example of CH4 mentioned here. So CH4 is methane, and as you can take a look at the structure of methane, the valence bond theory initially suggests that carbon forms four bonds with hydrogen by promoting one of its electron from the 2s orbital to empty 2p orbital. So initially its electronic configuration is 1s2, 2s2, 2p2, but to form bonds with 4 hydrogen, it needs to go to the first excited state with 2s1 and 2p3 configuration. And now since it has 4 unpaired electrons, it can create bonds with 4 hydrogen atoms. Now what you can take away from this is that this diagram suggests that we have one SS and 3 SP bonds here. So theoretically you will say that 3 bonds are identical while one is different, right? Wrong. This is not correct. However, in reality, all 4 bonds in CH4 are equivalent in every respect, which means the bond length is same for all 4 carbon hydrogen bonds and the bond energy is also identical. So, this observation leads us to a problem with your valence bond theory, and this is where hybridization comes to play. Hybridization explains that the carbon atom actually mixes its 2s and 2p orbitals to form 4 new equivalent orbitals, and these hybrid orbitals are called sp3 orbital. So instead of 3 sp bonds and 1 ss bond, we actually have 4 equivalent sp3 hybrid orbitals. Now we will try to go deep into hybridization and try to understand what actually is hybridization. So hybridization is the process where atomic orbitals of similar energy combine or mix to form new orbitals called hybrid orbitals. These new orbitals are of equal energy and similar shape, and they are used to form bonds in molecules. Hybridization is very significant for understanding of the molecular shape, bond angles, etc. The key point to remember here is that the number of hybrid orbitals formed always equals the number of atomic orbitals involved in the mixing. For example, if you have one s orbital and three p orbitals combined, they will form four sp3 hybrid orbitals. And this is exactly what happens in CH4. Coming to these key points of hybridization, which are very crucial for your understanding of this topic, so try to understand it. First of all, coming to the shape of hybrid orbitals. So, shape of hybrid orbitals uh, directly dictate the molecular geometry, as the hybrid orbitals are the ones that participate in the bonding. So, it gives the molecule its overall shape. Also, you know that s orbital is spherical shape, p orbital is dumbbell shape, and d orbital has complex shape. But here, what we do in hybridization, we consider a common shape for all the hybrid orbitals. Moving to the orientation of stability. So, hybrid orbitals have a natural tendency to orient themselves in a way that minimizes electron-electron repulsion, and this helps in stabilizing the molecule. Example, in case of sp3 hybridization, the four hybrid orbitals arrange themselves in a tetrahedral shape to be as far as possible, which creates a 109.5-degree bond angle, which is their most stable configuration. Moving to the next slide. As you were saying, hybridization is the intermixing of atomic orbitals of same or nearly same energy to form new orbitals of identical energy and properties called hybrid orbitals. So hybridization can involve different types of orbitals: half filled, empty, or even fully filled. All of them. All of them can participate in hybridization. The number of hybrid orbitals that are formed is directly related to the number of atomic orbitals that we are mixing. So to understand this, you can uh, consider like you have one s orbital, it is mixing with two p orbitals, and three hybrid orbitals will be formed. So 1, 2 resulting in 3, which we saw in sp2 hybridization. Coming to the association with sigma bonds, so hybridization plays a significant role in the formation of sigma bond and lone pair. And it is important to note that hybrid orbitals are directly involved in forming sigma bonds, which are the first bonds formed between atoms in a molecule. So while hybrid orbitals create sigma bonds, pi bonds are formed independently through the interaction of the leftover p orbitals. Come to the next point, that is naming of hybrid orbital. So as you can see, S and P are combining to form sp, S and P2 are combining to form sp2. So you can observe the trend and say that the hybrid orbitals are actually named after their parent orbitals involved in the formation. Moving ahead to the types of hybridization. Yeah. So the types of hybridization. So starting off with the first, that is sp hybridization. Sp hybridization will involve one s, one p, and then intermixing will take place, and we can observe a 180-degree bond angle that is formed here and a linear geometry. The second type, and an example of a linear hybridization or sp hybridization is BEF2. Second is trigonal planar. Trigonal planar geometry is obtained in sp2 hybridization. sp2 hybridization involves 1s and 2p orbitals. Example is BF3, and the bond angle formed is 120 degree between them. Geometry is trigonal planar. Coming to the next type, yeah. So next is sp3 hybridization. In case of sp3 hybridization, we have 1s and 3p orbitals. The bond angle formed is 109 degree and 28 minutes, and the geometry is tetrahedral. Example of tetrahedral geometry is CH4. The next type is sp3 dehybridization. In this hybridization, we have one s combined with 3p and one d orbital, which results in sp3 dehybridization. As you can see here, the geometry is trigonal bipyramidal because we have three bonds that are formed in one plane and two bonds that are formed perpendicularly. So three bonds have a bond angle of 120 degree, while two bonds have an angle of 90 degree. Example of this geometry is PCl5. Next type is octahedral. Octahedral geometry has the hybridization sp3d2. In this, 1s combines with 3b and 2d. So we have hybridization of sp3d2. All the bond angles are 90 degree, and example of sp3d2 hybridization is SF6. Moving ahead to calculating the Z score. So Z is actually the number of sigma bond plus the lone pair on your central atom. So as the value of Z, we get a corresponding hybridization. Let's say Z is 2, so hybridization would be sp. Z is 3, so the hybridization will be sp2, and so on. So try to understand with this example. Let us take the example of SO3. In SO3, we have 3 double bonds. So one double bond means 1 sigma and 1 pi bond. So we have here 3 sigma bonds because we have to only take into consideration sigma bonds and lone pairs. So we have 3 sigma bonds, hence Z is 3. So the hybridization is sp2. Similarly, you can see in the below examples of H2O, SO42 minus, PCl5 and SF4. Moving ahead to this trick. So this is a shortcut trick which you can use to calculate the Z score more easily, and in this you not need to draw the structure to calculate the Z score. So the trick says that Z is equal to half of number of valence electrons on the central atom plus negative charge plus minus positive charge plus the number of monovalent atoms H, F, Cl or Br. So let us try to solve this using an example here. So let us take N in NH3. So N in NH3 refers to like N has 5 valence electrons, and as you can see the number of monovalent atoms is 3. So it is half of 5 plus 3, which is 4, and this is its Z, and hence a sp3 hybridization. There is no negative, no positive charge in this case, hence we have not taken them into consideration. Similarly, you can see in the rest of the examples. That's it for today's lecture. And in conclusion, I would like to say that understanding chemical bonding is the key to understanding the structure and behavior of molecules. I hope today's lecture has provided you with a clear understanding of these concepts and the significance of this topic in study of chemistry. Keep practicing these techniques and they will become invaluable tools in solving complex chemical problems. Thank you. That's Ansh Shrivastava from NIT Raipur.